everyone. Oh, that worked. I didn't accidentally kick anyone out of the waiting room. I'm gonna say we could start like the introduction in 2 minutes or so, just so.
Okay.
2 to 3 minutes, just so we don't cut into the presentation time. Should be okay.
Yeah, sounds perfect.
Hopefully we will see all of Professor Miller's class come to this. He said,
Oh, where they're like black shirts.
no, he told them that they would get 8 bonus points for coming and listening to him twice today, because I think they also have class.
Like participation points.
Yeah, or something. Yeah, that's smart. So that'll be good. Are there a lot of first years in your class, Professor Miller? Just curious to see if we'll get more members for poly.
There are mostly first years, I would say. I actually have 2 undergraduates. I think someone from engineering, and then of the 16 people, I'd say the bulk of them are first year graduate students. I don't think I have any second years in there. Most people, well, maybe.
Take it their first year?
Yeah, most people will take it their first year, even though, the polymer people, of course, take it the last year, and then the organic people, a number of them will take it as well.
Okay, so welcome everyone. Just to make sure we stay on time today and also have enough time for questions, we're gonna go ahead and get started. So just as a reminder, my name is James Young. I'm the incoming Vice President of Poly PMSE here at UF. And today we have 2 talks, one from Dr. Corley from the University of Delaware, and then one from Dr. Miller from here at UF as well. Just another reminder, the next talk, which will be our last talk for the summer, is going to be on Tuesday. So let me go ahead and stop sharing so I can introduce Dr. Corley. Okay, so Dr. Corley is a distinguished professor in the Department of Material Science and Engineering and Chemical and Biomolecular Engineering at the University of Delaware. Her research centers around mechanically enhanced multifunctional materials inspired by nature. She received her BS in Chemistry and Engineering at Clark Atlanta University and the Georgia Institute of Technology, and completed her PhD at MIT under the advisement of Professor Paula Hammond and Gareth McKinley. She began her career in 2007 at Case Western Reserve University and held the Clamo Associate Professorship of Macromolecular Science and Engineering. Professor Corley is the director of the recently awarded Energy Frontier Research Center, Center for Plastics Innovation, the co-director of the recently announced Materials Research Science and Center at the University of Delaware, the Center for Hybrid, Active, and Responsive Materials. She is also the principal investigator for the NSF Partnerships for International Research and Education. Dr. Corley continues to have numerous awards, but with that, I'm going to turn it over to Dr. Corley so that she can tell us more about her research.
Wonderful. Thank you so much for the invitation to speak today, as well as the kind introduction. So I'm delighted to share a bit about a longstanding project in my group, one that excites me and really kind of encompasses, I think, what my group is really interested in. But first, what I'd like to do is share kind of the overall theme of my group. So if I'd given this talk about 3 years ago, this title would just be bio-inspired, but now it's bio-inspired and sustainable material systems. And to me, that's an indication of our growth as scientists and engineers as we are really kind of probing new areas of research. So my group is really centered around 4 kind of major themes. One is on using natural materials to think about ways we can utilize some of the understanding of dynamics. So to create things like supramolecular networks and blends. So those range from elastomers and elastomeric composites all the way to interpenetrating networks. We also have work really on innovations around manufacturing and design of material systems, one being reinforced hydrogels, and then also using multi-layer co-extrusion as a pathway to make scaffolds for tissue engineering, as well as making hydrogel systems. Most recently in my group, I've really focused since the move to the University of Delaware on looking at sustainable material systems. So the EFRC, Center for Plastics Innovation, is really focused on innovations related to upcycling and recycling of plastics material, focusing primarily on the complexity of plastics waste, new catalytic innovations, and then how do we upcycle these into novel material systems while also embracing circularity. We also have a strong interest in looking at bioderivable material systems. So using lignin as a feedstock, how do we make new thermosets and thermoplastic materials that have high performance that matches traditional plastic systems? We also have quite a bit of work on responsive materials, so generating things like bilayer actuators that are motivated by, say, pine cones and other actuating materials in nature. And then what I'll talk to you about today is our interest in spider silk and the hierarchy of that material. So I'll start by, really introducing what really motivated me and excited me as a graduate student. When I think about spiders, I'm actually allergic to spiders. Ironically, the only time I ended up in the hospital besides the birth of my daughter was when I was bitten by a spider as a graduate student, but still fascinated by the diversity of its function. So you may have heard that, a pencil thin thread of spider silk can stop a 747 in flight. You've heard about, all of the different types of silk that can be spun. So everything from the viscid silk to the dragline silk, and really understanding this organization of the components. So you have this macro scale fiber spider web that we run into and get annoyed by in the corners of the room. And if you go in a little deeper, you'll see the fibrillar structure of the silk. And then you have these crystalline beta sheets that are flanked by these amorphous segments. And then if you go down on another level, you'll think about the beta sheets and the hydrogen bonded beta strands. So you can think about this from the micro scale to the nanoscale. One of the things that I don't mention here is that it's not only the structure, but also the manufacturing that the spider does that gives rise to its unique toughness. But we're really interested today in thinking about this hierarchy and organization, where from a synthetic standpoint, we can take these building blocks. So, a variety of different amino acid structures, or we can then build up at another level to the secondary structure and then influence long range ordering. So this is kind of the theme of what we would like to do today and what I'll show you from several PhD students. So I mentioned this diversity in mechanical properties that are driven by the unique function of spider silk. So this is a stress strain curve that shows that with only slight modifications in the amino acid sequence, but also in how it's organized, you get a variety of different mechanical behaviors. So you can have something that's much more extensible, but has a low modulus, to something that's quite brittle, but then also has a high modulus in these systems. So for the work that we're interested in doing now, we really wanted to think about, what does this look like? And to me, this looks like a thermoplastic elastomer. And I was working on polyurethanes as a graduate student. So I started to think about this idea of how we can take these building blocks as a way to create these regions of different levels of order. So for example, for this particular type of silk, it has less ordered beta sheets and then highly ordered beta sheets, all in an amorphous matrix. So for the work that we're interested in doing is taking advantage of the multiple phases of a thermoplastic elastomer like a polyurethane, where you have these hard segments that you can use to control some of the dynamics. The soft segment, of course, you can use to control elasticity, but can we tune the soft segment organization such that we can capture some of these regions of varying degrees of order? So that's the motivation. In our first generation of systems, we wanted to ask a very simple question. Can we retain secondary structure and demonstrate that we can achieve hierarchy in these segmented polyurethanes? And I'll remind you that we're interested in solid state behavior for these material systems, which is an unusual approach to thinking about polypeptide systems. So here we have a soft domain, and in this case, our peptide is actually the endpoints of a soft domain, which is either PMSE or a polyethylene glycol. And that'll be important in terms of how we use these to build up levels of order. Our hard domain is comprised of either HDI or IPDI plus butanediol in these systems. And you can vary the types of peptides that can be used. In our first example, we use polybenzyl L-glutamate or PBLG in PDMS as our soft segment. And we made a couple comparisons, one using a crystalline hard domain, which would be HDI, or an amorphous hard domain, which would be IPDI in these systems, and varied whether we had a peptide or not. So either PDMS or PDMS PBLG as a triblock. Want to draw your attention to two things. One is that we can process these. So, one of our first questions is, can we actually make films of these? And the answer is yes. So we can make these either via solution casting or through melt processing of the films. We can find these to be only beta sheet structures. So in this case, we use the basically the block length with an N less than 10, which should give you primarily beta sheet structures. And the AFM images at the bottom actually demonstrate that we do have some phase segregation in our systems. The next question that we wanted to see is really, are we achieving this hierarchy? So we saw images of weak phase segregation, which from a long range order standpoint, looking at the small angle X-ray scattering, which is consistent, is very typical of polyurethane ordering. From a short range ordering, though, we saw two things. One is that for those systems that had peptide included, you actually were able to retain the beta sheet structure, but you also were able to see the hard domain organization in these systems. Now, how does that translate to mechanical properties? Because we started out thinking about how hierarchy influence mechanical properties. If you draw the comparison between just our amorphous hard segment and whether it has a peptide or not, or the absence of a peptide, you can see that the inclusion of a peptide actually gives you a much higher modulus than its PDMS control. But you have a substantial decrease in the overall extensibility of these systems, which then leads to a lower toughness. And we believe this is because of stress concentrations. The student who was working on this said He was stuck between a rock and a hard place with these material systems because there's a lack of lubrication between the heart segment and the peptide. So how do we overcome that? So we put on our polymer science and polymer chemistry hats and said, can we now decouple the hard domain from that of the soft domain? And in that case, we moved from the chain extended peptide systems to the non-chain extended version. And in this case, you take your peptide with PDMS and you use just PDMS to control the peptide weight fraction in the system. So this is the overall synthetic scheme. In this case, we're looking at two different peptides. We're looking at PBLA and a lysine-based system. In this case, we are also looking at two different block lengths. N equals 5, which should give you primarily beta sheets, and N equals 20, which should give you a mixture of alpha helical structures that can be modulated by the composition. So we varied our composition from 5, 10 to 20. And here the comparison is with PBLA, you have side chain backbone interactions. With lysine, you can have side chain interactions. So we wanted to look at, are we able to use this mechanism and still build up sufficient molecular weight to be above the entanglement molecular weight? Again, thinking about how we can form films and potentially fibers from this system. So you can see that these are all, well above the 35 kilograms per mole in these systems with dispersities that are consistent with that of a step growth polymerization. We then used ATR, FTR to look at secondary structure in these material systems. So as anticipated, based on what we know from literature about the peptide structures and their impact on block length on secondary structure, for both the PBLA and the lysine systems with a block length of 5, regardless of the composition, you had all beta sheet structures. What does change is the balance between parallel and anti-parallel beta sheets. Now, I will say the anti-parallel beta sheet structure is the most thermodynamically stable. And you can see that as you increase your block length, you are capturing more of the more stable beta sheet structure. For the 20 series, PBLA and polylysine, you see that as you increase the amount of peptide that's included in the system, you actually are increasing the helical content in the material system, while also varying, of course, the beta sheet parallel to anti-parallel structure. So we were able to achieve the secondary structure control that we wanted in this second generation of materials. We also wanted to look at the architecture of these systems, the morphology of them. So here we can see a couple of things that are happening. For both PBLA at the 5 composition, so whether you have a block length of 5 or 20, but a composition of 5% of the peptide in the non-chain extended PE, you can see short and random fibers. As you increase the peptide content, you then move to more long range but random fibers. And then at the highest composition, which is 28%, you see a denser fiber network. And we believe this will have impact, of course, on the overall mechanical properties of the system. But from the second generation, we really were able to confidently say that we can control secondary structure using this polyurethane framework, that we have molecular weight that's sufficient for forming nice films and then fibers I'll show a little bit later, and that we can now control the packing behavior overall microphase segregated structure. Now, the emphasis here is not on being able to actually derive a specific type of mechanical property, but just to show the diversity with all of these different handles we have with this dynamic framework. So here you can see for both the PBLA series as well as the polylysine series, that you're able to both modulate the extensibility as well as the overall modulus of these systems through the control of both peptide block length as well as the composition of these systems. So with this in mind, what we wanted to then think about is, can we now change the connectivity in these systems to be able to further control this hierarchy with the goal of really satisfying the space, much like spider silk. So we wanted to make a comparison with both linear systems and those made from a network. So still using PBLA as our system and PDMS, but now changing how we connect with the heart segment. So here we're using, this is a synthetic scheme, but the real point here is that we're using an HDI-based Desmodor crosslinker, so it's a trifunctional crosslinker, as our node points in these systems. Nicely, you're able to, you see in the picture on the left, we're able to make really nice and flexible transparent films. Here we're sticking to beta sheet structure. So PBLA has a block length of 5, and we're controlling the composition 10, 20, and 40. I'll remind you a bit about thinking about this parallel versus anti-parallel beta sheet structure. So for our linear systems, as we anticipate, you're able to control the anti-parallel content as you increase the composition. But you'll notice that for the network systems, no matter the composition, 10, 20, or 40, you only have parallel sheets, parallel beta sheets. And these parallel beta sheets are not the most thermodynamically stable structure. And this is really due to the synthetic consequences of how we actually build up our covalent network in these systems. Basically, you have N-terminus to C-terminus of the systems, which then forces it into this parallel beta sheet conformation. Now, what are the consequences of this? So our linear system, as I showed on the previous slide, has a really nice, highly dense, percolating fiber network system, which gave really nice mechanical properties. However, our network system, driven by this fact that we have these parallel beta sheet structures, actually forms more globular structures. And you can see here in terms of drawing a circle around these, this is really identifying why you get more of these globular structures in the system. And we would anticipate that they would have very different mechanical properties, which is true. And so a couple of key points here. I won't go through everything, but as we increase peptide loading for both the linear and the network systems, you actually see that the modulus increases, as we would anticipate, much like when we showed in the first generation systems. For our network systems, you not only get an increase in moduli, but you also get an increase in the elongation at break, which is not typically what happens in these systems. You have one at the sacrifice of another. And the reason why we're doing this, the reason why we're able to achieve this increase in the elongation at break is because we're increasing the molecular weight between crosslinks, because we're adding in more of the peptide to modulate the composition. Now, also very important here is that, of course, the linear systems tend to have higher overall mechanical properties than that of the network systems, except for the 40 system. And that's because of the way we're able to build up the overall microphase segregated structure. On the right is just a comparison of some hysteresis studies, acyclic experiments. You can see here that based on these competing physical and covalent interactions, you have very different hysteresis behavior. So in keeping with that theme, we wanted to now think about ways in which we can further modulate the hierarchy in these systems. So we were really excited about going back to the first phase of this work, which was thinking about non-chain extended, chain extended systems. So as a graduate student, I worked on chain extended polyurethanes and was really intrigued by this ability to promote either phase segregation, which is in most cases what you want, but then also be able to tune phase mixing that can occur between the two different systems. So we wanted to now think about, can we tune this soft block such that we can promote either hard and soft block interactions or interactions between the soft block components. So we wanted to now switch to a polyether system, again, polyethylene glycol, which could interact, have associated behavior with either the soft block peptides or with the hard block. So in this case, we turn again to creating our tri-block structure, polyethylene glycol as our middle block. And then here we're using lysine. And because we're using, I can just say in advance, the application for this was gels that we could use for biomedical applications. So that's why in the lysine gives us some tunability with environmental conditions. So in this case, we make our tri-block structure using N-carboxy anhydride polymerizations. And then we make our non-chain extended systems. So that gives us our first comparison. If we then use 1,4-butane-diol, we can now make our chain extended system where we build up both the soft and the hard block with the identification shown at the bottom. In this case, we're focused on the alpha helical materials, and we've chosen a repeat unit length of 20 for our lysine. And what we're modulating is the overall peptide weight fraction. So there are a couple of things that come to mind when we start to think about these particular systems. So one is we always want to try to understand this idea of what's happening with the soft block in terms of secondary structure that's occurring here. So we are wanting to use solid state NMR to look at the beta sheet to alpha helical content. So for our Z20 PEG Z20, we actually have about 85% alpha helical structures. One thing to note is that when we're making these systems, we actually use a DMF, which is a helicogenic solvent, to promote a higher fraction of our alpha helical structures. Now, a couple of things emerge with the non-chain extended systems. You can see that you increase. So once you place it into this non-chain extended system, to this polymeric framework, you actually have a decrease initially. So at 20 weight percent, you have a decrease in the alpha helical content. By the time you reach about 60 weight percent, you've recovered to close to the original value of your starting soft block system. In the chain extended system, you have a similar picture that merges here. So you have 39%, much lower than that of the pure soft segment, but you can see quickly at 36% and then at the close to 60%, you actually are able to surpass that of what you have for your pure soft body. And we believe that that is due to differences in phase associated behavior. And so one of the ways that we wanted to explore that is used differential scanning calorimetry, shown here at the bottom. So these are all exotherms up. So here, if we want to look first at the non-chain extended systems, you can see for the PEG HDI, which is our control non-chain extended polyurea, you actually see here that you have a PEG melting transition, 86% crystallinity at this case. For your Z2020, you now have a reduction. You still see the PEG melting transition, but you see a reduction to about 52% crystallinity. You see a slight shift that occurs for the Z2040 to a lower melting transition, and then you also see a lowering in that crystallization behavior. By the time you see the Z2060, you have pure phase mixing between that of the PEG and the lysine structure in these systems. So you have a confinement of soft interactions. And this is facilitated by the fact that PEG and the lysine can form similar helical conformations of a 7-2 helix, and in that way they can actually organize together. For the chain extended systems, a very different picture emerges here. So you have for the PEG HDI butanediol, which is the chain extended polyurethane, you can see really nice phase segregation. You have a PEG melting transition, and then you also have a hard domain with multiple melting endotherms. If you would anneal this, you would be able to most likely get to a single melting transition. At Z2025, you still see the PEG melting transition, but you do not see the hard domain interactions. So this indicates that there is some phase mixing, most likely with the lysine with the hard domain, so the HDI hard domain. For the Z2036, you can start to see the emergence of your hard segment crystallization peak, but you now have an absence of your PEG transition peak, which means that you have more phase mixing between within the soft phase than that you have between the soft and the hard phase. For the Z25, you now can start to see that you have you have phase mixing that occurs within the soft domain, And then now you are having a heart segment crystallization peak much higher than that even of the control system. Again, lending itself and aligning well with what we see in the ATR, FTR, where you have phase mixing with the lysine and the PEG, and then you're able to have a pure heart domain. So how does that impact mechanical properties? That's one of the most important things here. So for our non-chain extended systems, again, engineering stress versus engineering strain, the PEG crystallinity is really driving the overall mechanics of the system. So as the PEG crystallinity increases, that means you have a higher modulus, which correlates well to what we see on this graph, where the green curve, which has the highest overall peptide fraction, you can start to see that you have a reduction in the modulus, but a higher extensibility in the systems. And this is really driven by the fact that you have this really strong network system. For the chain extended systems, it's the heart segment crystallinity that is driving the overall modulus increase in these systems. And so you can see here that the highest modulus actually occurs for the control and that of the Z2050, which has this really nice heart segment crystallization peak or melting transition here. And so here you're able to see that you do get a reduction in the overall extensibility that is really driven by this increase in the heart segment crystallinity of the system. So this really does show that with this framework, by controlling interactions between either soft-soft or between soft and hard, this allows you to control the overall mechanics of the system. Now, the last piece that I'll share with you is really about how we can now build up this overall hierarchy. So we have some design rules of being able to tune these associations between the different phases. So here we can use covalent cross-linking as another handle to tune these. So we use the same strategy that we used with the PBLA, but now we're using polyethylene glycol with a lysine system. We're now actually looking at both beta sheet and alpha helical structures, but we're limiting the overall peptide content to about 20%. And that's really to drive both solubility and then to really allow us to make some comparisons between systems. So I really, really love this particular slide because I think to me, it really shows that we've been able to achieve this degree of hierarchical organization that we were so excited about. So if you look at our control, you can see really nice Maltese cross patterns. You can see in the optical micrographs at the polarizing optical micrographs in the top. You can see in our SEM that you have really nice spherolytic structures with different types of grain boundaries that are there, interfacial interactions, and really nice fibular structures. For the Z510, they are similar in structure as our control in terms of the spherolytes, Maltese cross patterns, the size of the crystallites, and you can start to see really nice interfaces that are emerge and nice fibular structures. When for the Z5 system, if you go up to the 20, you see a more diversity in terms of the Maltese cross patterns and the spherolytic sizes and structures, which is really driven by this phase mixing that occurs in these materials. So you have more of a diffuse interface, and that's why you have more of a globular types of structures with a mix of fibular structures in the Z520. For the Z2010, you have much larger spherolytic structures with really nice sharp interfaces in these systems, really driven by this whole overall segregation behavior. And again, AFM shows really nice phase morphology. For the Z2020, you also see changes in the overall spherolytic organization, really sharp interfaces and nice phase segregation. So now we can think about this film architecture and the mechanical properties, which are really dependent on the secondary structure and the peptide content. Now, how do we think about using this understanding, not just to make films with a diversity of mechanical properties, but to take advantage of some things that we know about solvent casting to tune the structure in these materials? So one of the observations that my graduate student made was that if you use DMF for these systems, again, this is a helicogenic solvent, that if you cast films from these covalent films, you actually have selectivity for the alpha helix on both sides of the film. However, if you use THF, you actually have one system. One side of the film forms a mixture of alpha helix and beta sheets, whereas the other one is primarily the beta sheet structures. And with that, you generate a bilayer morphology. And what does that give you? So when you expose this system, which has a mixture on different sides, you actually are able to generate actuating material. So it curls up into a really nice spiral structure, all driven by the fact that you can use solvent to self-select with each side of the film. And we've shown that depending on the secondary structure, get very different mechanical properties of these systems. So here it just shows that mechanical impact with DMF, it's all crystallinity driven. In THF, it's a mixture. So you have very similar moduli of these material systems. So there's an impact overall on how we can use this to drive mechanical behavior. The last thing is I'll just highlight here that we're working in a collaboration to start to think about ways we can take this idea of controlling secondary structure and place them in other network systems. So we started to think in collaboration as part of this NSF PIRE that I'm in, how we can work with folks to think about these for amphiphilic co-networks, where you have a hydrophilic and a hydrophobic phase and a co-continuous morphology. And these are used in a variety of different applications, such as puncture-resistant breathable membranes and extended wear soft contact lenses. So here, this is with Nico Bruns and his graduate student in his group, Sarah, and my graduate student in my lab, Dasul, where you can go through the traditional process of making these hydroxyethyl acrylate, PDMS amphiphilic co-networks, and forming and fabricating these APCNs. But we wanted to now change that, where again, hydrophilic and hydrophobic phases, and I'll skip to the next slide. And you can see the comparison here of the traditional APCNs. You have a much lower, you have some diversity in the overall strain, some changes in the moduli, but when you add our peptide structures, so these are PDMS, PBLA5, so these are beta sheet structures, you have a wide range of mechanical properties. So now you can have much higher moduli, and then also some very nice extensibilities up over 300% in these systems. So we're preparing a manuscript on this, and this really is due to the interactions that you can have between phases as you add in more and more of the peptide structures. Some other things that we are doing is I mentioned to you that we wanted to be able to make fibers from these, so we can show really nice electrospun fibers, and the fact that depending on the size and the composition, you have very different secondary structure conformations, which can be tuned by the peptide content. We're also making CNC peptide building blocks. The goal here is that we're making now water responsive shape memory materials. And then on the right, on the right, this is a recent paper from our group where we've shown that you can have really nice shape memory behavior that is controlled by both the beta sheet content or the alpha helical and beta sheet content in these systems, where there's an influence on the intermolecular or intramolecular interactions on both fixing as well as recovery in these shape memory systems. And with that, I thank you for your attention. And I must, of course, give all credit to the students who are in the lab doing the work right now. This is Dasul Jang and Jessica Thomas, and of course, my collaborators within the NSF PIRE who've been working with me on these projects, and also the funding from the NSF PIRE program. With that, thank you very much for your attention, and I welcome any questions.
Perfect. Thank you, Dr. Corley. So we do have a few questions. So first of all, this person is wondering why is it favorable to use PDMS over other biodegradable polymers such as polycaprolactone, et cetera?
Yeah, so great question. The original thought for starting with PDMS is that when we first designed this project, we really wanted to choose something that would cause the most phase segregation, right? So PDMS, we know from the polyurethane literature, would give you really nice phase segregation so that we can now start to build in our understanding by knowing which interactions we could have. So PDMS was just the right choice to be able to ask those fundamental first questions. But there are other systems that you can use that would be, may also have an enhanced phase segregation, but that was for us. We wanted to start with the one that would give us the most bang for our buck.
Perfect. Okay, so this one's a little long and might be a couple parts, but I'm going to make my way through it. So have you considered using semi-Vitrumer type systems in which you could have covalent adaptable networks? Free amines may interfere with the amide backbone, but other exchangeable systems such as cysteine, thiol, disulfide exchanges to the beta sheet sections.
Yeah. So great question. So for these systems, so the answer is we've considered it in a slightly different way. So for these systems, we wanted to stick to this framework because I felt like it would give us the most connection to industrial applications. This framework of these traditional polyurethanes for some of the applications that we wanted for coatings and other things, which would be, I think, a little more aligned with, the industrial interest in this work. From the standpoint of making systems that are adaptable, we are interested in non-isocyanate polyurethanes, which also allows you to capture some of this adaptability, much like what you've described. So stay tuned for that work. But yes, it is something that we're interested in.
Perfect. So that is all the questions that we have, which is excellent because we are just on time. So again, if everyone could give a round of applause for Dr. Corley. Oh,
Dr. Miller.
Dr. Miller, do you have a question?
I do. Thanks for letting me ask, so I don't have to type it in. So you mentioned this earlier that there is a connectivity of your tri-blocks. It essentially goes from C to N, then your soft block, and then from N to C. Is it even possible, and would you learn something if you made the C to N, then your soft block, and then C to N, so that the directions of your hard blocks were actually the same? Now, I don't know I think that's possible because polymer chemists can do most anything.
Right.
But I don't know if you would learn something in making that switch, essentially switching one of your hard blocks from one end to the other.
Yeah. So I think that assuming that it's possible, and as you said, we can design most anything in the polymer realm, right?
It will be harder, but I think you could do it.
Yeah, I think that there are some things to learn in terms of connectivity of if you could switch to these more thermodynamically anti-parallel beta sheets. By doing that, you should be able to promote more of a fibular organization, which would give you better mechanics. There's also the opportunity in some systems to be able to provide perhaps a little bit more by changing the connectivity, much like what I showed in the very first generation of these systems, is providing some lubrication and difference between the kind of hard and the peptide structure, such that you could potentially have a little bit better stress transfer in these systems. So, yeah.
Okay, thanks.
Perfect. Well, if we could all give one last round of applause for Dr. Corley. Thank you very much for being here today.
Thank you.
And with that, I'm going to turn it over to Sophia Goodrich to introduce Dr. Miller.
Okay. Hi, everyone. For those of you who aren't familiar with my face, I'm Sophia Goodrich. I'm the president of the University of Florida PMSE chapter. I'm really excited, I think, to see some new faces in this seminar series. And if it's because you're in Professor Miller's class, that means you go to UF. So feel free to check out our PMSE events that are upcoming this semester. So to start off, Professor Miller received his bachelor's and master's in chemistry at Stanford University under Professor Robert Weymouth. He went on to receive his PhD at the California Institute of Technology under Professor John Burkaw, doing his research on metallocene-mediated olefin polymerization. He then completed a postdoc at MIT with Professor Richard Schrock on the design, synthesis, and application of asymmetric ring-closing metathesis catalysts. He began his career in 2001 at Texas A&M and moved to University of Florida in 2007. His research efforts are focused on sustainable, environmentally friendly polymers with the goal of designing, synthesizing, and characterizing new biogenic polymers. His success led him to co-found a startup called Bioplastics and Florida Sustainables. And a few highlights of his accolades include the 2018-2020 UF Term Professor and 2018 Anderson Scholar Faculty Honoree. So with that, Professor Miller, I'm excited to hear more about your research.
All right. Well, thanks you, Sophia, for that kind introduction. And it's great to be invited to such a great summer series to sort of fill the gap in our collective lives. Yeah, thank you very much. So the title of my talk, which I failed to provide previously, is Ocean Digestible Bioplastics. So I'll give you some idea about the directions that our group is working in. And to start off, I will introduce just by explaining the magnitude of worldwide synthetic polymer production. It's over 400 billion kilograms per year presently. And to give you some idea about the volume of such materials, we are literally making a mountain's worth of polymers every year. So there's El Capitan. It's about 3,000 feet from the valley floor here. And that sphere of polymers that weighs 400 billion kilograms, it's a little bit taller than El Capitan, if you've ever seen this mountain in California. So it's quite a bit of material. And to give you another perspective, I've plotted here the mass of the human beings on the Earth. I think we're getting bigger, but we're also getting more numerous. And my prediction is that in the year 2027 will be the year when, and there's probably 8 billion of us or so, the mass of polymers produced will equal the mass of human beings on the planet. Turns out in North America, we use more than our own body weight in plastics per year anyway, but the rest of the world is catching up. And that's the reason for the steepness of this curve, this yellow curve here, that seems unsustainable in some ways. So we try to address some of these issues and ask questions about how are we going to get this kind of material in the future. Well, what happens to this 400 billion kilograms of polymer that is produced every year? Well, a little bit is recycled, a little bit is incinerated. The most likely destination for a piece of plastic nowadays is in a landfill. And then if you think about the mass balance here, there's about a third of the material we're not really sure where it goes. And we know where some of that ends up, and that is in the middle of the ocean. So waterways dump into the ocean, and there's really an astounding amount of plastic floating out there, being disintegrated into smaller microplastics. And this is a video taken from the middle of the Pacific Ocean. So there are visible pieces out there simply floating around. And various calculations try to estimate the amount of plastics that we're somewhat accidentally adding to the oceans as a function of time. One of them is 15 tons per minute. So some of these are alarming. I happen to think that there's probably more plastic out there than what we're presently appreciating. But scientifically and as a polymer chemist, we try to address some of these issues and ask, well, why can't our polymers be more water degradable? Most of these polymers were designed essentially, a couple of generations ago, and they weren't really designed for the idea that they may need to disappear someday rather than be persistent in the environment. So the Washington Post sort of tongue-in-cheek made fun of this article. Good job, humans. The ocean contains now 5 trillion pieces of floating plastic, in addition to all the tiny microplastics that are suspended in the ocean. But the Washington Post contributes to this problem all the same. Sometimes their paper arrives in a low-density polyethylene bag, which floats and will contaminate the ocean, just like the plastics you saw. In some ways, I liken this to the ozone hole problem. Some of the younger people don't know that this is a problem, or it's still a little bit of a problem, but it was a bigger problem when I was growing up. And chemistry sort of solved this, right? Instead of using chlorofluorocarbons, we largely switched to fluorocarbons. which lacked the chlorine. And it was a chemistry problem that didn't seem to impact our quality of life that much. Unfortunately, fixing the plastic problem will probably impact our quality of life a little bit if we end up changing the kinds of plastics we use. It's about a 2 orders of magnitude larger problem in terms of economic scale, polymer chemistry versus refrigerants and aerosols and things like that. But it is something that I think can be solved by chemists and, of course, a lot of money. So in our research group, we do target sort of the next generation of disposable or short-term packaging plastics. And polymer chemists have done a pretty good job of building these kinds of materials from renewable feedstocks. Maybe a little bit harder is it to make them degradable. So biodegradable, water degradable, there are different kinds of degradability out there. And quite possibly the biggest challenge to the chemist is to do these things and also make them inexpensive. So if they're not cheap and can't compete economically with incumbent plastics, they won't be adopted. And so your research may be fundamental and interesting, but it won't solve a standing problem. So I'll talk a lot today about our efforts to install these weak links into various polymers, sometimes by design, sometimes unwittingly. And these weak links allow polymers to break down to oligomers. Now, once they're oligomers, they're probably not microplastics, they're probably less of a problem, and they also become food for things that are in the ocean or on land or wherever we're attempting them to disintegrate. So we want first there to be some mechanism that's really abiotic to go from a polymeric material to something that's more molecular. After that, we are sort of hoping or expect that those small organics end up being food for something which will ultimately turn them into carbon dioxide and perhaps complete the cycle. Now, polylactic acid has been advertised as a potential replacement for many, many plastics. It does have drawbacks. I think most of us are familiar with these kinds of materials. I have loads of this stuff in my office. I don't know if you can see the shelf back there. That here's a PLA cup. You can even get the PLA straws now. And it does have drawbacks, as I mentioned. One of them is it has a low glass transition temperature. This is a photo my student took of trying to make tea in one of these cups. And if you put hot water into one of these cups within a second, it will undergo plastic deformation because of its low glass transition temperature, approximately 55 degrees. Your typical coffee is in the 60s in terms of degrees Celsius, maybe even hotter. And so this material is unsuitable for hot food or hot water applications. It also has surprisingly slow degradation. So although it comes from corn and fermentation products, lactic acid, I'm showing here a video of a cup that's been sitting in my backyard for 7 years for strange reasons, but I put this, actually it's been close to 8 now. So here is a video of the cup after 2 years sitting in a swamp. I essentially live in a swamp here in Gainesville, Florida, but you can see things are growing in and around it. There's water around it and it is not degrading whatsoever. After 7 years, this is the same cup. It looks maybe a little bit hazy on the outside, but it would still hold water. A newer addition to my collection in my backyard is this PLA straw. Haven't looked at it recently, but I suspect it will have the same slow degradation process. Another issue is that it's a food-based feedstock insofar as it uses corn out of Nebraska primarily for its synthesis. So because of its slow degradation, there's now a relabeling a lot of this material called industrially compostable rather than naturally compostable, because if it doesn't degrade in my swamp, it doesn't degrade in a lot of other places. So if you send it somewhere and pay them money, they will force it to degrade, but who wants to heat the plastic and feed enzymes to it just to make carbon dioxide? So it is not all that water degradable. It's not as biodegradable as people had originally thought. This is just a mention of a review paper that we wrote a couple of years back, where we highlighted a number of efforts to achieve this quest. So various research groups have been able to make bio-based plastics. Separately, you can make high glass transition temperature plastics. And one of the ongoing goals out there is to make high glass transition temperature polymers that originate with biomolecules. So that's kind of an ongoing goal and does encapsulate a lot of the the work in my research group. We've worked on aromatic biopolymers, so bioaromatics, and then installing rings into polymer chains in order to increase the glass transition temperature. So I'll talk quite a bit about those two topics today. I'll start here or continue here by asking, what is the most abundant polymer linkage functional group out there, and therefore probably the most degraded one? And the answer to that, it is the acetal functional group. Acetal functional group is the connecting functional group for cellulose, which is a fairly persistent material, for starch, which is designed to be a less persistent material, for glycogen, which is sort of the animal form of starch that we use for rapid energy availability. Other structural components like chitin are all connected by acetal functional groups. This is the oxygen, carbon, oxygen functional group. Nature has done a very good job of using this functional group to make a very wide variety of materials. Our commercial enterprise has not. So if you ask yourself, well, who's making money off the acetal functional group in polymer realm? The answer is not very many people, and to a very small degree. Polyoxymethylene, which you'll note as a Keck clip, it's also made in little plastic gears. It's introduced as a plastic replacement for metal in the 50s by DuPont. So that's one example of a polyacetal, although as you know, if you're an organic chemist, these things are extremely hydrophobic and fairly resistant to even things like concentrated sulfuric acid. Another polymer out there that is based on an acetal functional group, albeit it's not in the main chain, is polyvinyl butyrol. So this material is used in packaging and a few other things. It's very good for making films. And in fact, when you take polyvinyl alcohol and acetylize it with butyraldehyde, you end up with polyvinyl butyrol, which is what is the most commonly used polyacetal out there. And it is used in safety glass. Essentially, it provides a plastic, very transparent interlayer between sheets of glass. So in the case of breakage, the material tends to hold together. So we are interested in polyvinyl alcohol as a starting material, not really because it's bio-based yet, although it could be, but because it's water soluble. And as a water soluble polymer, it probably won't be a microplastic in the ocean. And there's a fair amount of evidence suggesting that polyvinyl alcohol could be biodegradable. It certainly won't float around in the ocean again, because as I mentioned, because it's fairly water soluble. It's certainly at high temperatures, as you'll know if you ever put these little pouches in your dishwasher. And so what we started with this project was to attach bio-based aromatic aldehydes to polyvinyl alcohol instead of sort of this flexible aliphatic aldehyde. And when you do that, you get a very large boost in the glass transition temperature. So here's vanillin, which is, of course, primarily a synthetic molecule, but still about 15% of the world's vanillin is made from the lignin of Norwegian spruce trees. So it is a bioavailable molecule, not particularly cheap. And you can attach that to polyvinyl alcohol. This is the attachment shown in a closed NMR tube. So it doesn't really have to be driven. You can get up to over 70% acetylization in a closed system here with 10 equivalents of vanillin in the course of, 17 hours or so. So its synthesis is not particularly challenging. You can get a reasonable amount of acetylization, and you do increase the glass transition considerably, all the way from about 75 to 142 degrees, which of course would widen its thermal application envelope. So here is a graphic showing the attachment of a wider variety of bio-based aromatic aldehydes to polyvinyl alcohol. In all cases, we see an increase in the glass transition temperature. Vanillin is here, VV at 142. So there's a boost in the, again, a considerable boost in the glass transition temperature. You can make some correlations with the structures of these. So there's some hydrogen bonding that's residual in some of them. Some of them have some flexible groups like this ethoxy group, which probably introduces some free volume, which gives you the lowest glass transition temperature of this series. But nonetheless, we can see that we are able to boost the glass transition temperature into a realm that's quite useful, right? Could in principle hold very hot water, most of these. We did another test where you can subject this to polyvinyl alcohol, commercial polyvinyl alcohol starting materials of different molecular weights. If you buy a higher molecular weight polyvinyl alcohol, you do see a slightly higher glass transition temperature, but it nonetheless tends to be around this 140 something degree temperature range. So we can throw these at a variety of conditions. Not surprisingly, if we throw them into fairly acidic aqueous conditions, we do see hydrolysis. If the pH is 1 or 2, you get essentially complete hydrolysis in the course of a day. At pH 3, hydrolysis is incomplete, but nonetheless measurable. But at pH 5 or pH 7, we really don't see any substantial hydrolysis over the course of a day. And we've done some longer experiments, but the polymer is pretty resistant to neutral water conditions, be it deionized water or, for example, seawater, which we also use as a medium for our degradation studies. But nonetheless, this seemed like a way to take a relatively inexpensive polyvinyl alcohol, which shouldn't really contribute to the polymer contamination problem, attach a bioaromatic aldehyde, utilize it for its high glass transition temperature, and then somehow take it back to the starting materials. So where on earth would this be useful, and how are you going to get this to degrade in the environment? There's not that many places on earth where the pH is low enough for this to happen, but this bird's stomach is one of them. So this bird ate a bunch of non-depolymerizable, non-degradable polymer. Had this bird eaten exclusively our polymer, it probably in the course of a day, because its stomach pH is around 2.5, it probably would have turned the polymer back into polyvinyl alcohol, which is water soluble, and vanillin, which is tasty and probably somewhat easily metabolized. Probably wouldn't have killed the bird. So subsequent to attaching these bioaromatics, which are somewhat available but somewhat expensive, we wanted to try to attach a variety of ketones, making polyketals from polyvinyl alcohol. And so we attached many of these. Not all of them would attach. For example, camphor and menthone are essentially too bulky, we think, to attach to any substantial degree to polyvinyl alcohol, but most of the others will attach. Acetone was of particular interest to us. It is very inexpensive. It is very non-toxic. My PhD advisor always said it's less toxic than ethanol, but I've never done a shot of acetone. But an acetone, although currently not it's not presently a bio-based molecule, it can be. So there are several fermentation routes to making acetone from, say, cornstarch. So it is something that is potentially quite sustainable, and again, fairly non-toxic and also inexpensive. So as I mentioned, we attached many of these to polyvinyl alcohol. Here's a waterfall plot of, again, a closed NMR system, where in the presence of 30 equivalents of acetone, we get about a 68% acetylization. That means 68% of the OH groups are now occupied, by ketones. It's a ketalization process, and some 32% of them remain unattached to acetone. And this does, in fact, change the properties quite a bit. You can see here in the middle with acetone in the middle of this plot. It gives us a glass transition temperature of 100 degrees. So we're pretty excited about that because the TG essentially matches or slightly excels the TG of polystyrene. And it's a comparably inexpensive material made from polyvinyl alcohol and acetone. Two things are fairly inexpensive, maybe slightly more than polystyrene itself, but nonetheless in the same realm for its economics. And you can see that there are a pretty wide variety of polyketals shown here. There's a polyacetal hiding up there from furfural also, which incidentally gives the highest glass transition temperature. Zingerone's a little bit floppy, so it gives a glass transition temperature lower than PVA itself. And also you can see here the degrees of now ketalization vary somewhat, largely in line with their steric bulk. Sterically bulky things just are a little bit hesitant to make those kinds of ketals. We can dry them a little bit by water removal. We can make films out of these materials. So here is commercial polyvinyl alcohol. It's pretty clear. Commercial polyvinyl butyral, which I mentioned was an interlayer glass material, pretty clear. Our polyvinyl acetone ketal, also pretty clear. So these are solvent cast films, which we're able to make, some with more skill than others, but nonetheless, these seem to be pretty reasonable and strong, tough film-like materials that could potentially be used. So what about their degradation? So if we throw this polyvinyl acetone ketal in low pH aqueous media, such as pH 2 or pH 3, we see a pretty rapid hydrolysis, almost complete hydrolysis in the time span of 24 hours. But at pH 5, with deionized water or seawater, we essentially see no hydrolysis after a day. So the ketals are surprisingly stable under even pH 5 conditions, maybe a little bit surprising. So we did a longer term experiment. So a day is a day. It's just a day in the life of a graduate student, but let's try this for longer. So on the left-hand side, we see our fairly acidic conditions, pH 2 and pH 5. And as I mentioned, after a day, we see essentially complete hydrolysis of these polyketals. At pH 5, complete hydrolysis is seen, but not until 6 months has transpired. You can see a picture here. In deionized water, we still see the little piece of plastic. In seawater, we still see the little piece of plastic. But after 5 months at pH 5, little piece of plastic is gone. Seems to be dissolved. It's turned back into water-soluble polyvinyl alcohol and acetone. So we continued with the experiment to understand if water and seawater are capable of hydrolyzing polyvinyl alcohol, this polyvinyl ketal made from polyvinyl alcohol. And the answer is probably yes. And you can see this 2-year data point. And yes, we ran this for 2 years before we finally submitted this paper. And if you believe these numbers, it seems to be about a 3% hydrolysis rate after 2 years. Okay, so we're probably changing the properties a little bit. Maybe it's speeding up a little bit with additional OH groups appearing in the polymer backbone. So rather than doing the 3-year experiment and waiting longer to publish, I asked my student, Yukai, well, why don't we just heat these? Okay, we'll simulate time in both deionized water and seawater. We'll simulate the passage of time by heating them. And we just decided to heat them to 80 degrees. So they're in a hot water bath at about 80 degrees. And what we see is that after 3 months, both in seawater and deionized water, they're almost completely hydrolyzed, certainly to the point where you don't see them anymore. The little plastic chunks are gone. If there is any ketalization, it's not impacting the water solubility of these materials. They seem to be water soluble, so they're no longer visible, right? So if they're in the ocean, certainly in a warm ocean for a long period of time, these polymers should in fact essentially disappear, and then hopefully biodegrade once you get to the polyvinyl alcohol stage because of its water solubility. Now, what does it mean to degrade at 80 degrees in 3 months? I'm not sure, but you can do some very gross calculations by understanding the kinds of barriers that are present. And I estimated in this paper, it was about 16 years, plus or minus a decade, in order for a polymer like this to degrade in the ocean, maybe a warm ocean. It's going to be slower in a cold ocean. But in a warm ocean, you might end up expecting these things maybe to degrade in 2 decades. That's a lot better than polyethylene and polypropylene, which probably will last 500,000 years, very long period of time in the open ocean. So going back to this idea of increasing glass transition temperature, which is a goal of ours, PLA kind of stuck with a TG of 55 degrees, water bottle plastic made from fossil fuels, a TG of around 72 degrees. That's a little bit better. We've been working quite a bit with bioaromatics, including this ferulic acid material, which is kind of interesting. You can get it from nature. It's actually sold as a vitamin supplement. So I won't talk too much about ferulic acid today, but it is something that we've been working on. And when you make this polydihydroferulic acid, or PHFA, you get a TG that looks a lot like that of PET itself. One of the problems is that even after bargaining on Alibaba.com, you're still paying about $45 per kilogram for ferulic acid. So it's not all that cheap. And if you buy these vitamin supplements, it's about an order of magnitude more expensive than that to buy it in the tablet form. So that's never going to compete in a commercial in the commercial realm for making something that is so simple as to just hold water. So what we want to do is take the design strategy and essentially have a ring. So we believe that rings, and I think it's well appreciated that rings in polymer chains limit conformational freedom and therefore tend to boost glass transition temperatures. We want that ring in the polymer backbone, but we want something that's probably a hydroxy acid, and we want it to come from sugar. Okay, so it doesn't need to be dirt cheap, but it needs to be sugar cheap. So it needs to be something that is relatively inexpensive and not $45 a kilogram. So we got some inspiration from my friend Tatsuo Kaneko in Japan, and he had worked on taking this very inexpensive itaconic acid molecule, which is a sugar fermentation product available at a little over $1 per kilogram, so that's well under $1 per pound. He attached ethylene diamine to it, which of course made this amino acid, which then he could polymerize to make polyamide, which is a very attractive glass transition temperature, 154, maybe some degradation properties. We like esters in our polymer backbones because we believe that ultimately esters are a little more hydrolyzable than amide, let's just say. So the design change here is not a drastic one, but we want that to be an OH group instead of an NH2 group in order to get to our hydroxy acid that is cheap and can be polymerized to a polyester. So the molecules I've shown here in the green ovals are not new. They've actually been reported in patents. The polymers on the next page I'll show are new. For some reason, nobody ever made the really simple polymers from these. But we ended up making these in water. The bottom one is really easy to make and isolate. It is a diacid, so obviously that's an AA type monomer. We're going to need a BB comonomer to go with it. The top one, although it's really easy to make, is very hard to isolate. So don't try this at home, but we have some tricks in order to isolate that molecule. But it is a hydroxy acid, kind of like lactic acid, and has some potential for being homopolymerized, which we've done. But it is challenging to isolate that particular molecule, although it's not particularly hard to make. So if you take that hydroxy acid and polymerize it, you get this homopolymer, again with this EBPC diacid molecule, which is a lot easier to make and isolate. You have to co-polymerize it, and we've done so with a variety of diols. And you can see here, our molecular weights are not terrible, but pretty good for us in terms of these typical step growth polymerization reactions. The glass transition temperatures when the ethylene spacers, the alkaline spacer is short, tend to look like that of PLA. So PLA is in the 50s. We get maybe 60, 62 degrees for the TG of some of these. So in terms of glass transition temperature, it looks quite comparable. If you add more methylene spacers in your comonomer, you only serve to ruin your glass transition temperature. That needs to lower it about by 5 or 10 degrees per additional methylene group. So in general, you want to use ethylene glycol with this in order to keep the glass transition temperature high. So what about their water degradation? Well, this was an interesting experiment. So we tested these in acidic media, but then, of course, we test them just in neutral water. And what we found was that in neutral water, after about a month, that the polymer seemed to swell. It didn't really look like a chunk of plastic anymore. It looked more like a swollen mass. And so it did form a gel after about a month. And as we continued this experiment and measured the molecular weight by GPC as a function of time here, we found that after a year, essentially 360 days, that the number average molecular weight, if you will, was pretty close to our lowest standard. So essentially was hydrolyzing. And the polymer was losing its mass fairly rapidly in the course of a year, even though it's just a simple polyester with an amide peroldinone ring in it. In air, however, even though we live in humid Florida, the mass loss was, I think, measurable and real, but not as rapid. Okay, so you have a mass loss of maybe 10% here in air over the course of a year, kind of the material that you might use for dry packaging applications, where in air it lasts a decade, but when someone throws it into the ocean, then it disappears in a year. We can actually take an NMR after a year to see what's going on here. And in fact, we do see regenerated ethylene glycol. We do see regenerated diacid monomer, looking exactly like the authentic monomer before we started the whole process. And by integration, we see about a 94% ester hydrolysis after the course of a year. So this thing has essentially gone to dimers and maybe a few trimers after the course of a year, just sitting in water, orbital shaker, under neutral conditions. We don't have a great, well, we have a little bit of idea as to why this might happen. If you are an organic chemist and have worked with a lot of solvents, you might appreciate or have used N-methylprolenone, which kind of looks like that part of this polymer. And you'll note that N-methylprolenone is a water miscible organic solvent. And so it's obviously very hydrophilic. And so we think that that particular portion of the backbone of the polymer is fairly hydrophilic. It draws water in, causing the gelation. Now, of course, your rate is going to be 0 if your concentration of water is 0 at your ester group. But as long as the concentration of water is not 0 because of this gelation process, you can maybe reasonably expect some hydrolysis of that ester group. We'll come back to this towards the end of the talk as to how we think this is happening. It's pretty different. It's pretty similar to PLA, but at the same time, because of the amide group, fairly different. Both PLA and this polymer are alpha substituted polyesters, but PLA, of course, doesn't really show any water degradation over long periods of time. It's just not that hydrophilic. So we've also moved on to another class of bio-based molecules, terpenes. A lot of people work on these as sort of starting materials for making a variety of polymers. So alpha pinene is a fairly inexpensive terpene. There's a pretty large demand, surprisingly, for camphor. So rather than extracted from camphor trees, there is now a synthetic protocol that takes alpha pinene, which is far more abundant and available in tree sap and pine trees. And you can convert alpha pinene to camphor. And because of this commercial production, this commercial demand for camphor itself is a fairly inexpensive commodity at about $3 per kilogram. Okay, so maybe less than $1.50 per pound. We and others can oxidize camphor with nitric acid to camphoric acid. And so now you have a diacid, which of course looks like something very interesting to a polymer chemist. And we have made a variety of polyesters from this. So in our first studies, we simply copolymerized camphoric acid with a variety of alpha omega aliphatic diols. With ethylene glycol itself, you get a TG of about 51 degrees. Okay, again, very similar to the TG of polylactic acid. If you use longer diols, you just have lower glass transition temperatures, probably less useful as a packaging plastic. This reacts fairly well with erythrotan and isosorbide, although these are both secondary dialcohols. So there's more steric encumbrance there. They seem to polymerize reasonably well with these. Erythrotan is a molecule that we've used a fair amount. You can make it pretty easily from erythritol, which you buy from Amazon. It's in a lot of foods nowadays as a lower 0-calorie sweetener. It's in nature, so I hope it's pretty benign because I consume a decent amount of it. Isosorbide, most of us are familiar with that as a glucose product, and both of them can be incorporated, copolymerized with camphoric acid. And in that case, you have a more rigid diol that you're employing with 1 or 2 rings in it, and you get TGs of around 100 or 125. So those are interesting from that standpoint because you get to really boost your glass transition temperature from fairly, from a terpene and from a sugar as feedstocks. So what about their degradation? I don't think we're expecting too much from this, but my student Olivier came back to me and said, well, after 2 weeks, they're gone. What do you mean? Well, here's a little chunk, and then the little chunk of plastic after 2 weeks, either pH 1 or pH 2 or deionized water. I'm not sure we measured it after. Here's just the 2 week. I don't think we measured it after a day. Although you can see the little glob of polymer down there. Apparently it's fairly well depolymerized. And when we look at that little glob by GPC, we have a polymer that's lower than our lowest PMMA standard. And so things seems to have completely depolymerized just in neutral conditions in deionized water, which is kind of unusual for a polyester, right? Again, polylactic acid does not do that. So we wanted to figure out maybe why this is happening and what makes this possible for for an ester. So we looked up some literature about the hydrolysis of a very simple ester here, methyl acetate. Okay, so methyl acetate, you can study its hydrolysis. You can, of course, hydrolyze, you can undergo the first step of hydrolysis, which is hydration of an ester. That first step is to make this hydrate of an ester. And that seems to be the slow step in generically speaking, on the pathway to full hydrolysis. Of course, you can hydrate with just one water molecule. That'll have a higher enthalpy barrier, but a lower entropy barrier because you only use one molecule. Computationally, the sweet spot is to use 2 molecules of water. You have this relatively favorable, enthalpically favorable 6-member transition state. Of course, you have to bring 3 molecules together to accomplish that. So this barrier is fairly high, 40 kcal per mole for delta G double dagger, which means it's really not going to happen at room temperature, which is why you can use methyl acetate near water and nothing happens, or at least one of the reasons. We wanted to look at this type of computation, so we mimicked it here at a different basis set and different level of theory, but got the same result. So you end up with a delta G double dagger and a delta S double dagger. Overall, the barrier is about 40 kcal per mole. And essentially, the reason why this is not a favorable process is because you end up with a large amount of charge concentration, that is positive charge concentration, on these hydrogen atoms, which are not part of the 6-membered ring. Okay, so you have a lot of charge buildup, and nature abhors charge buildup. You can see that here in this electrostatic potential map by these blue dots. So the blue portions just mean that you don't have, you've got charge concentration. You don't have a situation where charge is delocalized, and that costs energy coulombically. So what about our polymer? Well, our polymer is not methyl acetate. It is, in fact, if you look at it, it's a polymer that's really one molecule with a whole bunch of bases in it. Okay, so you've got lone pairs everywhere. Every ester group has lone pairs, which can conceptually function as a base, maybe in a base catalyzed process. So this first transition state shows the approach of one proximal base coming up to this water molecule and taking away that large positive charge that otherwise would tend to build up at this hydrogen. Okay, so that positive charge is delocalized by the carbonyl oxygen of a nearby ester group. Now, this has maybe an advantage of being built from camphor. Now, camphor is a cis, stereochemically, it's a cis diester, diacid formed into a diester here. And so maybe it's particularly easy because of that stereochemistry involved to bring that carbonyl group up close to this water molecule. But bringing just one of them, what does it do? Well, you don't really change the enthalpy that much. It's about similar enthalpy, maybe a slight decrease in the enthalpy penalty, a it's more enthalpically favorable. Barrier goes down by 2 kcal per mole, but because you have some conformational restriction in this transition state, you pay a small penalty for the entropy. Altogether, you get about the same barrier when you approach this transition state with a single nearby ester group. What if we approach our transition state with a basic ester from the other side of our polymer chain? Well, that will dissipate charge buildup at this hydrogen atom, but of course not the other one. Got the same answer here. It's a little bit more enthopically favorable, a little less entropically favorable, and you get almost the same overall barrier. But what if you bring both flanking ester groups near that transition state, near that 6-member transition state? You get to attenuate the charge buildup on both of these hydrogen atoms that are exocyclic to this 6-member transition state. And you get to do, and when you do that, you vastly lower the enthalpy barrier. You can see the enthalpy barrier is about 10 kcal per mole lower. You do pay some entropy, but again, because it's a polymer, you're not paying all these translational degrees of freedom for the entropy of bringing these flanking ester groups nearby. You just pay a little bit of conformational penalty. So in a lot of ways, this looks like an enzymatic pocket where things are pre-organized. And it turns out that you get a reduction in the delta G double dagger by about 8 kcal per mole, which translates at room temperature to a millionfold increase in the expected rate of hydrolysis just at room temperature. So in some ways, you can call these polymers, self-catalyzing. They self-catalyze their own destruction. Doesn't seem to work out the same for PLA. PLA might just be too hydrophobic for this to work. Maybe the cup shape of this particular molecule is crucial for this pocket to form. We're still investigating those sorts of things. We can go back and remember the polylactams that we studied. They also underwent hydrolysis under relatively neutral conditions. And so we wanted to study that as well. And you really get the same answer here. You end up with an enzymatic type pocket. You end up approaching one of these water molecules with a flanking ester. The other water molecule is approached by the flanking amide functional group. Interestingly, with the nitrogen, I would have expected that to be less basic than the oxygen. I think this oxygen has conformational restrictions on what it can do, so it does seem to decide to work with the amide as the base. A little unusual, but nonetheless, you still get this pretty drastic lowering in the overall delta G double dagger. It's a lowering of almost 10 kcal per mole, which translates to about 10 million times faster rate of hydrolysis than you might expect for a regular ester. So again, this polymer seems to be catalyzing its own destruction. Couple slides here on a final topic that I will talk about. And it has to do with this multi-million-dollar USDA funded project here centered at the University of Florida. It's about 20 PIs over a couple of states who are studying this crop called Ethiopian mustard or Brassica carinata. It is a non-GMO crop, so that's interesting to some people. Its the main focus, the main reason this was funded is because carinata provides unusually long fatty acids in its bio-oil. Okay, so the bio-oil is about almost 40, it's over 40% of the mass of the carinata seed is a bio-oil. And then if you look at the fatty acid profile in that bio-oil, over 40% of that is erucic acid, about 42% erucic acid. Erucic acid is an unusual fatty acid. You don't want to eat it. Your body can recognize and metabolize C12, C14s, C16, C18s. You get much bigger than that, and your body doesn't want to metabolize them. So erucic acid is not very well metabolized by your body because it's a C22 fatty acid. But it's actually very good if you throw this into the production system for fuels, whether it be biodiesel or in our case, aviation fuel. It actually makes very good aviation fuel. So they've flown a couple of jets. There's actually been some transatlantic and trans-Pacific flights where they have used not fully, but portions of fuel made from this particular crop. The theory is that one day we'll all be flying on some sort of bio-oil. I don't know, maybe we'll have really good batteries by then. We'll be flying on essentially solar power. I'm not sure. But if we're reliant on liquid fuels, certainly seems necessary for very maneuverable jets. This crop or one like it very well may be grown everywhere. Australia and Qantas are very interested in growing this. They grow a lot of carinata to try to fly their planes to see if it will be the fuel of the future. If it is the fuel of the future, well, what else does this crop give us? Well, if you look carefully at what's in the seed meal, there's quite a bit of synaptic acid in there. If you grow this crop on 10 acres, you can seed 10 acres with there's a bag of seed right there that's about 50 pounds. You can seed 10 acres. From that 10 acres of land, you can fly an airplane, small one, from Florida to California and back. From that 10 acres, you can also get 150 kilograms of this molecule called synaptic acid, which is inside the seed meal, which is not part of the fuel that is not part of the fatty acid mix that is turned into fuels. So my student Stephen here has shown taking some of the seed meal and doing a base extraction. So after you do the base extraction, we can get really at least a 2% yield. It might even be higher than that if you do a couple of iterations, maybe a 4-5% yield in terms of mass of synaptic acid. Synaptic acid is actually comes from the Greek word synape, which is from mustard. So this molecule was named and sort of recognized in the early 1800s. They didn't know the structure. It's kind of reassuring to do an extraction on a plant-based material and get an NMR, which looks pretty darn good. This NMR looks kind of like our commercially available material. There's water and DMSO in there for extraction. But in large part, we get a decent looking NMR from this molecule, which is extracted maybe up to 4 or 5% from this, this seed meal. Ultimately, they like to feed the meal to animals. Animals, and like humans, do not love mustard, but if you take out the spiciness, they'll eat it. There's a fair amount of protein in the meal. So here's a sequence that we've done to make a polymer from sinapic acid. So we take the sinapic acid, we extend it with chloroethanol, which is not the greenest way to do it, but it is a way to do it. And we make this hydroxyethyl sinapic acid, which we can polymerize with antimony oxide, and we can make this particular polymer. Typically in large scale production, several gram production, we will use commercial, that is synthetic sinapic acid, which you can buy, I think from alibaba.com. We probably dropped $1,000 on this, which is fine. So it's not the cheapest thing out there, but it tends to make a polymer, this polyethylene sinapate, with a TG of about 118 degrees, which is good for us. This is actually a plant that we grew in our lab of this thing. So this is a movie my student made, not from that plant, but from the seed meal. We're able to go through this sequence. I'll say the hydroxyethylene sinapic acid looks pretty good. It's a nice white polymer, nice white powder. I'm sorry, it looks pretty good by organic chemistry standards. And the polymer is a little darkish. When we scale it up, it doesn't look quite as terrible. But that particular polymer is an actual example of a polymer that came, not all of the atoms, because we put this little extender on there, but almost all the atoms in there came from Brassica carinata, which is grown in the state of Florida, somewhere a little bit north of here. So that's a polymer that that is truly bio-derived. What else can we do with this? Well, depending on the extent of hydrogenation of the double bond. So nature gives you the double bond in the back, in that part of the sinapic acid. But if you hydrogenate it through standard methods, you can tune in the glass transition temperature. So if we have a fully hydrogenated version of this shown here by this orange repeat unit, you get a glass transition temperature for this polyhydrogenated ethylene sinapate of about 41 degrees. If you have about a 30% degree of double bonds still present in the backbone, you get to match the glass transition temperature of PLA. If you have about a 60% presence of the double bond in the backbone, you get to match the TG of PET. With a 90% presence of the double bond in the polymer backbone, you get to match the glass transition temperature of polystyrene. So you get to tune in the glass transition temperature from the same bio-based molecule. And I'll just briefly compare this to some of our previous work. I mentioned ferulic acid earlier, comaric acid. These two molecules are surprisingly abundant in sugarcane bagasse. This is a pile, it's probably about 10 meters tall. This is a pile of sugarcane bagasse in the state of Florida. It's the largest single sugar mill on earth, and they make a lot of sugarcane bagasse, which they burn for energy, but you can also get ferulic acid and comaric acid out of those. So those give polyethylene ferrolate and polyethylene coumarate with slightly lower glass transition temperatures. You get, for polyethylene ferrolate, you get 113. For polyethylene coumarate, you get 109. So it seems like what we're learning here is that by adding 1 or 2 methoxy groups, you get a slight boost in the glass transition temperature of the corresponding polyethylene coumarate, ferrolate, or sinapate polymer. So that just leaves me to some conclusions here. Our polyacetals are water degradable, certainly with higher temperatures. Our polylactam esters seem to be fairly water degradable if you're patient enough, even under neutral conditions. And we've shown some reason why that might happen. Theoretically, the polymer might be undergoing self-catalyzed base hydrolysis. That seems to be our best explanation presently. This also happens with the pure polyester, as we found with this kind of specialized polyester that comes from camphoric acid. So that just leaves me to thank students in the group who worked on this over the years. Some of the papers are a few years old, some of them just came out. This was the pre-COVID group photo way back from October 2019. So several of these people have moved on. I've gotten 3 new graduate students since then. I do especially want to thank the National Science Foundation for funding a lot of this work, and then also the USDA for funding our Spark project on the Nebraska, Carinata. So thank you for your time. And I will attempt to answer any questions that you might have.
Great. Thank you so much, Professor Miller. I can get started with a few questions, but feel free if you have questions to type them in the chat, and then I will relay them to Professor Miller to be answered. So I'm just curious what molecular weights sort of need to be achieved in order to display material properties that resemble the synthetic polymers you're trying to replace, and how difficult is that to achieve with these renewable resources?
That's a good question, and the bane of our existence at times. We have a general target of 10,000. Now that's a very broad term. It really has a lot to do with entanglement, molecular weight. And once you're there, you get TGs, which are fairly representative. We saw even with our polyvinyl alcohol polymers, around 20,000 going to 160,000, you still see a couple of degree increase in the glass transition temperature. But if we can get to a number average molecular weight of 10,000, and we certainly haven't done that in everything I've presented, but if we get around there, then we're pretty sure about the TG, at least within a few degrees. And we always think it's a plus or minus 10 degrees anyway for TG measurement, but it's a good question. We get some molecular weights of 60,000, some MNs. Sometimes we're stuck at 6,000 and just can't do better, in which case you don't really believe the TG. Molecular weight is definitely something we have to work at.
This it's such an important field, though, because you showed in the beginning the way things are going. It's really important we start considering different kinds of polymers. So I appreciate the work that your group is doing, and I had one other question, because I'm lucky in that the polymers I make, it's pretty easy to get the starting materials. And I'm just curious, are there certain challenges with having to use these feedstocks or these like renewable resources to try and get them in a form that you're then able to make these polymerizations?
Well, so that is an issue. I mean, a lot of people just, they buy lignin and they compound it and they make something. And as a chemist, that's kind of hard for us because we have a hard time characterizing them. As a polymer chemist, organic chemist, we love to take our polymers, dissolve them in solvent, take an NMR. And if we can't do that, we're kind of unhappy and distressed. So ultimately what we do is we find a biomass source and we convert that to a molecular entity. And once you do that, you have some hopes of recrystallization, and then you're not really worried about exactly what its source was, because you can get it relatively pure and then use it as a monomer for making a nice linear polymer. So that's kind of our overall scheme, is to make nice linear polymers, rather than, which means you do generally rely on fairly discrete molecular things to start with. So that is there's different realms of where people make things. Some people attach things to existing biopolymers and they can make really cool materials that way. We like the idea of making melt processable materials, which generally means non-cross-linked linear polymers, because we want to injection mold them and form them into the next water bottle. That's sort of our area. And as chemists, we love to be able to dissolve our polymers and understand them, and understand really what they look like in solution.
Well, great. Are there any other questions? Anybody typing in the chat? Maybe not. I know we've reached the end of our allotted time. So I just want to thank both Professor Miller and Professor Corley for joining us this morning and presenting some great talks and research to consider. I look forward to seeing more from both of your labs. And thank you again for joining us. We have one last session of the seminar series next Tuesday, so I hope to see you all there. Thanks so much. Have a good afternoon.
Have a great day.